Hey AP Stats, we are looking at 11.1. We are beginning your last unit. So if you're not already there, go ahead and join me at 11.1. So I am going to move through this pretty quickly, and sometimes I'm going to prompt you to pause, but other times please feel free to pause if I'm moving too quickly. So we're going to jump right into the first example. So the Mars company makes a claim about their M&Ms, and it gives you a list of percentages, and that is their claim for the distribution of colors. So there was a sample taken, a random sample of one bag. It had 60 total candies in it, and you see the sample data there in the table. So if they claim that there are 13% browns, 13% are reds, 14 yellows, 16 greens, 20 oranges, and 24% are blues, how can we test this company's claim? We could, from our previous chapters, look at one color at a time, but the problem is when we do that, we are testing just one of the colors. We are not testing the company's claim of the entire distribution at one time. So now we have a new test. It is actually called a Chi Square Goodness of Fit test. So in the last slide you saw the sample data given to you in a table that is called a one-way table because there was just one sample there. And the Chi Square test for goodness of fit is to test to see if the observed sample distribution is different from the hypothesized population distribution. Okay, so our null hypothesis would be that the company's stated color distribution for the M&M milk chocolate candies is correct. So their proportions are correct, their percentages are correct. Our alternative hypothesis then is that the stated color distribution is not correct. So in general, this is how you would state a null and an alternative hypothesis for a situation like this, in which you are going to use a Chi Square Goodness of Fit test. Now you might be asking, could we list the null hypothesis as each of the proportions? So proportion of blues is 0.24, the proportion of orange is 0.20, so on and so forth. And you may do that. What I would be very careful with, though, is your alternative hypothesis. You would need to say that at least one of the proportions above is incorrect. So the idea of the Chi Square Goodness of Fit test is we are comparing observed counts from our sample with the counts that would be expected if the null hypothesis was true. So if their proportions are true, did the number of blues that we got compare to the number of blues we would expect to get? The more observed counts, the more they differ from the expected counts, the more evidence we have against the null hypothesis. So, assuming that the color distribution stated by Mars is true, 24% of all M&Ms produced are blue. So for a random sample of 60 candies, the average number of blue M&Ms should be 0.24 times 60, so 14.40. This is our expected count of blue M&Ms. Now you do not want to round that because it's an average over time. So if we wanted to find all of the expected counts, we could do that for each of the colors. Orange, the claim is that 20% are orange, so 0.2 times 60. The claim for green is 16%, so 0.16 times 60. Go ahead and pause and figure out the expected counts for the other three colors. Okay, you should have gotten 8.4 for yellow, 7.8 for red, and 7.8 for brown. That makes sense because red and brown had the same proportion. So if you notice, we've got our 6 colors, with a list of our sample data. That's the observed number or the observed count compared to the expected count, and you see that there are some differences there. So the big idea here is how likely is it that the differences this large or larger would occur just by chance in random samples of size 60 from the population distribution claimed by Mars? To answer this question, we calculate a statistic that measures how far apart the observed and expected counts are. The statistic we use to make this comparison is the Chi Squared statistic. So we have done the Z and the T, and now we are doing Chi Square. This is on your note packet, so just take a minute to look at that. If the observed counts are far from the expected counts, so your chi-square is large, there is evidence against H naught. Well, how far is far? Well, we have to do a significance test. Let's first calculate our test statistic by hand. So the table shows the observed and expected counts for our sample. Let's use our formula. So notice we have our observed, blue, is 9, minus our expected, 14.4. Square it, divide by expected, plus, now we will do orange. We observed 8, subtract our expected, which is 12, square it, divide by 12, and you can continue this pattern. If you sum all of those, you get a test statistic, chi-squared, of 10.18. Now we could use that to calculate a p-value. We could calculate with a chi-square CDF to find the area under the curve. That would allow us to perform a significance test. But we're actually going to wait because we can run the chi-square test and it'll give us the p-value all at one time. So, the big question, do these data provide convincing evidence? That implies a test that the company's stated color distribution for all M&M's milk chocolate candies is correct. So this goes back to our state, plan, do, conclude. So we will first begin with state. Please pause and tell me what you think the state is. Okay, so it should look something like this. We want to perform a test of, and then your hypotheses. H naught. The company's stated color distribution for all Mars milk chocolate candies is correct. So then the alternative, the company's stated color distribution for all M&M's milk chocolate candies is not correct. So what's the plan? Pause for a moment. Think about what you are going to do. So plan, we will do a chi-square goodness of fit test. It's called a goodness of fit test. At alpha equals 0.05 if conditions are met. I needed to specify that because they did not specify a significance level. So the question is, what conditions must we test? We begin with random and 10%. We took a random sample. It was 60 M&M candies. We can assume that 60 candies is less than 10% of the M&M population of candies. Number 3, this is the one that changes. So our large counts changes just like it does when we calculate or do tests for proportions versus means. We have another large counts condition here that is special to the chi-square test. It's that all of the expected values are at least 5. Now make sure that when you are checking your conditions that you actually list what those are. You cannot just say that they are all at least 5. So we had a random sample of 60 M&Ms. 60 is less than 10%, and the expected values are listed. All of them are larger than 5. So now we are going to do. We're going to do a chi-square goodness of fit test. take a moment to locate this in your calculator. The test that you are looking for is the Chi Square GOF, so goodness of fit. You are going to need to put the observed data in your L1, your expected values in L2, and you will need to tell your calculator the degrees of freedom. Now be careful on this. Your degrees of freedom have nothing to do with the sample size any longer. For the chi-square test, you actually want the number of categories minus 1 instead of your sample size minus 1. So degrees of freedom for this one, because there are 6 colors, 6 minus 1 is 5. Pause and put your data in L1, L2, and run a test. When you ran a test, you should have gotten something like this. It says chi-square is 10.18. It tells you P is 0.07. That is your p-value. This p-value is just like any of our other p-values, and chi-square is our test statistic. So look at this and make a conclusion. Since the p-value of 0.07 is greater than our alpha equals 0.05, we fail to reject H naught. What does that mean? We do not have convincing evidence that the company's stated color distribution for M&Ms is not correct. Okay, now one thing I do want to tell you is this CNTRB down here. This stands for contribution, and so they might ask you at some point to look at each of the components and figure out which one contributed to the chi-square test the most. And so think back to when we calculated that test statistic by hand, and all of those boxes came up in the different colors. Each one of those colors is a component, and so you want to figure out which one has the largest impact on your chi-square. Okay, so let's look at the graph. So a lot of times we have been able to use the normal curve to approximate our data, but the chi-square distribution is never going to look normal. It's actually always going to be skewed right. And so this particular graph here is a chi-square distribution with a degree of freedom of 5. You notice our p-value here is in the tail. Now, as your degrees of freedom increase, your distribution will become less skewed, so it will kind of even out here just a little bit, but it's still going to be skewed to the right. Now, on the next page of your notes, there is a recap section. I encourage you to do that. And then kind of at the bottom of that page, there is a describing a chi distribution section that kind of talks about the shape, the center, and the spread. So go ahead and take a few moments to read that.